Hello, everyone. Thanks for being here and joining this workshop. I'm Samin Aref, here from University of Toronto. I designed this workshop with a very diverse, range of technical backgrounds in mind. So it's going to be around 3 hours. For those of you who don't have, that much background in LLMs, first of all, that's perfectly normal because they were not such a big deal just 2 years ago. And hopefully the first 1 hour or 1 hour half of the workshop will be more relevant and useful for you. For those of you who have some background in AI, in LLMs, in text mining, hopefully the last 1 hour of the workshop will be more relevant where we get to the technical details. But I start from the very, very, very beginning. All right. So, but before I start, raise your hand if you know less than 2 people at this workshop. All right. So, okay. So maybe let's use one minute for everyone to just introduce themselves to the person sitting closest to them in the room. And also for the online participants, I think it would be useful if you try, sending a private message to another one of online participants so that we can, feel like a real class. That's what I often do at the beginning of all of my classes. All right, so maybe 1 minute for this practice while I give you some handouts. There you go. Of course. All right, so let's start with a very brief introduction. So hopefully these slides will be on things that most of you already know. So if it is too basic, just don't worry about it. We're going to have a quiz. So if all of these are too simple, then hopefully you will be among the winners of the quiz game, which is a Kahoot game, and I have some prizes for you. All right. So let me start with just some background info on machine learning. All right. Okay. So with traditional machine learning, we used to deal with tasks like this, using image data to classify, let's say, cats' images and dogs' images. So separate out whether an image shows a cat or a dog, right? And this idea was, useful for, quite some time. But the thing is, it was, rather data intensive. We needed, large amounts of labeled data to be able to, train these models. So we are talking about AI. AI is this, this very general field. Machine learning is a subset of that. Deep learning is a subset of machine learning. Generative AI is a subset of deep learning, or we can consider it as a subset of deep learning. And large language models are another subset of deep learning. And as you can see, they overlap with each other. So the main focus of today's workshop in the morning will be on generative AI and large language models. All right, so as I said, there are some challenges to, image classification. Here you see, some pictures of blueberry muffins and chihuahuas. And many of these, models, they do well on many things, but they were, surprising, moments of disappointment. We would expect, AI to be able to handle these. And I mean, these are not tough cases these days, but maybe up until, 10 years ago, these were like real challenges. All right, so here is another example, again, about traditional, machine learning, about learning from examples, just to set the room for, what I mean by classification. So here we have, medical images from biopsies, and there are, two types of, tumors. So each image represents a tumor, and there are benign tumors and malignant tumors. And the task was to build a system that can tell this apart from each other, right? And as you know better than me, pathologists and radiologists trained for many years to be able to, tell this apart from each other and tell a patient whether, the tumor they have is benign or malignant. So how do we solve this problem? I mean, with the traditional machine learning, we would solve it by, learning from examples, right? So that was the, the main idea. But what, these researchers did in 2015 was training pigeons to become doctors for telling apart these types of tumors. So before I show you, raise your hand if you think this idea works. All right. Raise your hand if you're somewhat suspicious of training pigeons. Raise your hand if you are sure that pigeons cannot give us reliable predictions on tumors. All right, a few, okay, so let's see. I mean, the study is published, so there must have been some outcome to this, fun exercise. So you can watch the video on this link, but also I think I have it here. So this is what they did. So it was for breast cancer images, and they would, first, the pigeon who was being trained would see, this white square to start. Then an image is shown to the pigeon. These are, labeled data, so we already know whether each image shows a malignant or a benign, tumor. And then the pigeon has a few seconds to decide, and then has two options: the blue, let's say the blue and yellow rectangles, they show, malignant and benign. And whenever the pigeon chooses correctly, the pigeon will be rewarded by a food pellet, right? And as the pigeon wants, is kind of incentivized with more food, it gradually learns, quote unquote, to tell apart, the images as correctly as possible to get more food. And let me pause and ask you another question. So pathologists and radiologists, they train for many years to, be able to, analyze and make decisions based on, medical images. But these poor pigeons only received trainings for like 8 weeks instead of 8 years. So considering the, the substantial difference in the level of education that was provided to them, what do you think would be the accuracy of these pigeons after they earned their doctorate after 8 weeks? All right, any number between 0% and 100% is a viable answer. Also, for online participants, please feel free to type in the chat any number between 0% and 100% that you think would be the accuracy of the pigeons to to classify these images? Good question, not 100%. So I don't have an exact number, but we know that there are you know, it is well documented that there are like serious mistakes in those lines of jobs as well, those lines of work. 60%. All right, 61, 62. All right, anyone else? 80%. So let's say that the data they had was, all right, so first of all, the assessment was done on medical images that the pigeons had not seen before. So this was not like cheating. It was a proper, you know, assessment of performance. So what do you think? Just a number between 0 and 100. 85. Also someone, Christoph, from the online participant says 85. Someone says 10%. Who else? Anyone wants to make a guess? 50%. I mean, let's say also the data was balanced, meaning that 50% of them were real benign, 50% were malignant. So a random guess would have an accuracy of 50%. Anyone else? So 85, I mean, it looks pretty good. I mean, I know that we complain about the healthcare in Canada so much. So 85%, like I would go to the pigeon doctor. I mean, and all the issues will be solved. All right, let's see. All right. If you haven't made a guess, you can make a guess and have it in your mind to then see how accurate you were. So, I mean, the pigeon is paying close attention. I mean, I really like to have the pigeon, you know, in like my class, undergrad class or something. All right, so yeah, 85 to 90% correct responses. Yeah, so this was, you know, just to show you this idea of learning from examples, but without code and without, you know, Python and this sort of stuff, because the fundamental idea is not necessarily about programming. All right. Okay. All right. So here are some, you know, common language tasks. Text classification is where we have text as data. Yeah, question, yes?
Is it any particular feature that
So I think we need to use the microphone so that also the participants can hear the question. Yeah, we have 16 participants online. So if I forget, please always remind me and others to use the microphone so that everyone is in. Yeah?
So the question is that whether there is a particular feature in those kind of photos which is very good, recognizable by the neural network of the pigeon, or it is just something that is generally able to learn in such a high accuracy. Because maybe sometimes it happens that the data set has a very particular feature which is well recognizable by a particular neural network. And maybe this is the case, and maybe if you train this pigeon with some other data, it doesn't get as high as this. Is that a particular for this data set or general?
Yeah, that's a great question. I mean, I wish I had the immediate answer, but you know, the study is published, and probably there are more information about, you know, the fundamental reasons why this idea succeeded. My impression is that you know, some animals have, you know, specific you know, skills. So maybe pigeons have like really good eyes, but I don't know more about that. That's just my speculation, but I'm pretty sure if you check the study, there will be more information. And it could be the case that this wasn't just a random setup of random animal and random task. Rather, they put some thoughts into it before doing the study. But still, 85 to 90% is quite remarkable. Microphone again.
So I'm wondering about the group of pigeons that were there. Were they selected progressively? So, or was the entire group trained versus you pick the winners from the talented pigeons?
That's another great question. To be honest, I haven't read the study. This is just a motivating example that I use in my classes. And the questions I typically get are not as tough as the questions I'm getting from this crowd. So I can see that you're very, very prepared for this workshop. But again, I'm pretty sure that the answer would be there in the study. But the thing is, if they had this kind of progressive step of only keeping the good pigeons, I think their assessment would be somewhat biased. And for the case that they were trying to make, I think it wouldn't be the ideal setup. So again, I guess that they've done the proper assessment just based on the average group and so on. Yeah. More questions? Are there more questions? No? All right, so the mic is there. And anyone who wants to ask a question, they can go and grab the mic, or otherwise signal me and I'll move the mic around. All right, so these are 4 main language tasks. Text classification is where we have text as data. For example, comments. In social media, let's say we have a data set of comments, and we want to classify them into different groups. So maybe positive comments and negative comments. So comments that have positive sentiment and negative sentiment. That would be a binary classification. Another common application for text classification would be classifying so-called toxic comments on social media, things that are problematic, racist and so on, as opposed to non-toxic, right? So this would be one common language task. Question answering is where the user asks a question from the large language model, and then the large language model generates an answer. That would be the more recent version of it, but maybe up until 10 years ago, question answering, there was also a form of it where the large language model has access to a larger paragraph or a larger piece of text, and the answer is somewhere in that piece of text. Then question answering was just about the language model kind of processing the question and deciding where is the starting word for the answer in that paragraph and what is the ending word. So just let's say highlighting a part of the already existing text that is likely to be the answer. Document summarization, I think, is quite self-explanatory, and text generation. So for text generation, of course, it could be about question, but also, when we ask a large language model for a piece of poetry or something like that. That's, the common usage I have. I always go for poetry. It never fails, because, yeah, there's no right and wrong. But for other things, I had many moments of frustration, asking for determinant of this 3x3 matrix. It doesn't work. All right, so this is a recent history of language modeling. As you can see, before machine learning era, it was like, very basic, kind of rule-based ways of dealing with language. Then you can see that in early 2010s, we had word-to-vec and n-grams. Then we had RNNs, which stand for recurrent neural networks, and LSTMs, or long short-term memory networks. So just to give you some ideas about RNNs from 2014, so the online participants would see, this part, hopefully, if it is not too small. So is it okay if I draw here? All right, so for RNNs, let's say that the text was something like the food was adequate but not great. So this is, of course, for us, it's easy to see that this is a negative food review. You know, if we see it on Google Maps, we can say that this is a negative review. But this was a challenging case back in 2014 for RNNs because they couldn't, you know, handle the interdependence between words and they didn't have the so-called attention mechanism, which we're going to talk about. So as you know, maybe, you know, adequate doesn't have a negative connotation, great has a positive connotation, and maybe this part would get lost because this is just a common word. So RNNs, at least the RNNs I know from, you know, 10 years ago, they couldn't handle this. They couldn't classify this to a negative class. Let's say we're doing sentiment analysis. We just wanted to classify each sentence to positive and negative. Despite that it is so easy for us to see that this is a negative review, RNNs from 2014 couldn't handle this. Long short-term memory networks, LSTMs, they were like an improvements of RNN to resolve some other issues, specifically the fact that they were, you know, very hard to train because of a numerical issue that we called vanishing and exploding gradients. So LSTMs kind of handled that small issue, but still they were not, they were sort of I would think of them as a duct tape solution to this challenge of the interdependence between words. Then we had attention mechanism in 2015. And attention mechanism pretty much, you know, was a breakthrough for language modeling. And we're going to talk about attention mechanism more. Then we had transformer architecture in 2017. Then the BERT language model in 2018, so from Google. So so for if I'm not mistaken, for both attention mechanism and transformers, I think there were some people from University of Toronto involved. So we are at the right place to talk about these recent developments. Then we're going to also talk about BERT, and more recently we had, you know, T5 and GPT-3. These are like models somewhat comparable to BERT. And then 2023 we had Llama 2 from Meta, and then Gemma from Google. So I suppose that you might have, you know, already tried, you know, some of these models. So let's just go to the next slide. So so I started with, you know, image classification. Now we're talking about language. This seems somewhat unnatural, but the thing is, actually, there was, you know, a very important connection between them. So a lot of the improvements we had in image processing are, you know, somewhat attributed to, you know, to the ImageNet competition and some excellent work from a professor of CS from Stanford, Fei Li, who kind of, rumor has it that she stopped, you know, her other projects and just, you know, spent, you know, some focused efforts on producing high quality, you know, labeled data. When, you know, when people were working with, you know, relatively small images, maybe, you know, 150 by 150 pixels, she was developing a data set for, you know, higher resolution images. So she was, you know, rather, I mean, a visionary. And because of that, we had, you know, the many advances in the field of image classification, including some of the very first, you know, deep neural network architectures. And then with transfer learning, many of those advances were kind of transferred from image classification field to language field. And now, of course, you know about ChatGPT. It was the fastest growing consumer application in history, and GPT-4 was trained on 1,000 terabytes of text from internet, and as you know, some lowered version of it can be accessed for free. This part is actually like pretty important, because there's so much hype about these models, especially when you read about them on, I don't know, LinkedIn. There are like a lot of exaggerations about the scope of these models, how they were developed, what they can do. So 1,000 terabyte is something that is, at least we can imagine it. One external hard drive could be 1 terabyte. We're talking about 1,000 of those. So this is a rather finite amount, and this is contradictory to a lot of information that is online, especially in like some business circles. This is another example of that. I remember seeing many posts about this, that when GPT-3 was already making headway, there were speculations about GPT-4 being this much larger, and it's going to solve everything. It's going to cure cancer and, I don't know, solve climate change for us. And here we are. Those problems are not solved. Yeah, I think it's very important to have some critical perspective on these new technologies, because the reality of the situation is this. So first of all, the parameter count would not really say how powerful these models are, and the increase in parameter count again is something that is imaginable. We went from this to this, of course, by some of the biggest tech companies in the world. This was something possible, and they did it, and it's not that big a deal, and we are still not there. And even if we get there, I don't think it's going to solve climate change and cancer and aging for us. All right, so what GPT-4 can do? Of course, there are, I assume many of you have tried it, generating new content. It succeeds in many natural conversations, provides some answers, sometimes better answers to what we used to search, using search engines. It does some decent job for programming tasks. It has some human-like cognitive abilities, like understanding jokes, or at least it pretends that it understands jokes. Pretending that it is self-conscious. Again, I guess the pretending part is important. And some artistic capabilities, like generating poetry or digital music. And also it can combine natural language and image processing, I guess. That was what I meant to write here. All right, but I think what is more important is what it cannot do. So I guess some of you might be familiar with this puzzle. So the puzzle is about a farmer, a wolf, a goat, and a cabbage. So the farmer must, cross the river and take, the wolf, the goat, and the cabbage to the other side. But the challenge is that the boat can only carry farmer and one other item, right? And if goat and the wolf are left unattended, the wolf is going to eat the goat. If the goat and the cabbage are left unattended, the goat is going to eat the cabbage. And the question is, how can they cross the river without anything being eaten, right? So this is a very a common, math problem. And there's a JavaScript simulation for it. So I can, share the slides later, and you can try the simulation. But this has, this has an answer, this puzzle, and of course, when we ask GPT-4 for the answer, it does give us the correct answer. So the correct answer is this. This is the solution. The farmer should take the goats over, then return empty-handed, take the wolf or cabbage, then return with the goat. So step 4 is the rather counterintuitive part that some people miss initially. Then take whichever item wasn't taken in step 3, then return empty-handed, then take the goat over. So there are in total 7 crossings, and these visualizations, they show the correct answer. So of course, when we ask GPT-4, it's going to give us the correct answer. Why? Because chances are it has seen it somewhere on Wikipedia from the data where it was trained on, right? But again, the disappointing part is when we slightly adjust the example. When we give GPT-4, at least up until a few months ago, when we say, all right, now you solved the puzzle, now I have a new puzzle for you. In the previous example, just consider that the rules of the games have changed. Now it is not the wolf that eats the goat, it's the cabbage that eats the goat. Just changing a variable. So it's just purely it's just a variable change, right? We just swap essentially name of 2 of these items, or we change one of the rules, right? And the answer should be immediate, should be immediately obvious, because if in the correct answer that it gave earlier, it just swaps all instances of goat with those 2 variables. If it swaps all instances of wolf with goat, then we get the correct answer. But the thing is, it cannot do it, or at least up until a few months ago, where this example was rather fresh, it couldn't do it. It would give the same answer. It started becoming apologetic for its mistake when it was pointed to it, right? So I think it's very important to acknowledge all these limitations, especially when we are when we are hopeful that we use generative AI for some high-risk situation, including many examples that we care about in this workshop. All right, here is another example. So this is from reinforcement learning, solving some human-generated simulation. So this is like a game where I guess this this boat can increase its score by I don't know, taking by going over a longer distance or something like that. And the thing is, the game has a bug in it, right? It has an exploit. It has a bug in it that there's a way of for the boat to just go in circle like this forever and just collect more and more points, right? So this is an example I typically use with my mechanical engineering students, but because I think, I think this is somewhat relevant. We have one of the former director of AI at Tesla saying that physics may also have some exploits, and we should be trying to find them to extract infinite energy. So from my naive perspective, where we are kind of putting the focus on the developments in this field is somewhat misaligned with reality. So of course, Tesla had major issues with the actual thing that it should do, which is having reliable cars that wouldn't, I don't know, explode. But you can see that the director of Tesla is interested in finding infinite energy through reinforcement learning because of these patterns that we have in the simulations. So let's see if we, I'm not sure if we have the sound. Just a second. All right, this should work.
I think it's possible that physics has exploits. I think it's possible that physics has exploits, and we should be trying to find them. Arranging some kind of a crazy quantum mechanical system that somehow gives you buffer overflow, somehow gives you rounding error in the floating point. We'll find some way to extract infinite energy. For example, when you train reinforcement learning agents in physical simulations, and you ask them to, say, run quickly on the flat ground, they'll end up doing all kinds of like weird things. In part of that optimization, right? They'll get on their back leg and they'll slide across the floor. And it's because the optimization, the reinforcement learning optimization on that agent has figured out a way to extract infinite energy from the friction forces and basically their poor implementation. And they found a way to generate infinite energy and just slide across the surface. And it's not what you expected. It's just sort of like a perverse solution. And so maybe we can find something like that. I think it's possible that physics.
All right, so again, to me, with my naive engineering background, I think solving, climate change or, making progress in the medical field should be like easier challenges to focus on rather than extracting infinite energy and solving the challenges of an automotive company to be able to, build cars that wouldn't explode should be something that we shouldn't even discuss because it's like from 50 years ago, right? But you can see that it seems there's like a misalignment of focus on in this field. All right, let's see if there's a question in the chat. Oh, sorry about that. So for the next questions, we will make sure to use the microphone. Maybe the microphone wasn't on. All right, so there are, of course, risks and limitations to this, these AI systems. They hallucinate sometimes. Their safety can be improved much more. Their risks are not immediately known to us or even the experts. They represent many forms of bias, and they are not aligned with human values, quote unquote. So about AI and the future of work, AI, it's been years that some forms of AI have already impacted human work. Some basic forms of AI, like automation, have already replaced some jobs and created some others. AI has already impacted many blue-collar and white-collar jobs and will continue to affect the human workforce. And I think the main idea here is that people who start using and incorporating AI, despite all its limitations in their work, are likely to be more efficient and more competitive. All right, so that was the basic introduction. Now let's move on to the game. So, all right, I think I have the game here. No, not this. I don't know how to minimize this. Okay, all right. So you can join the game. All right, I guess I need just a few seconds to log in and prepare the game. So also the online participants can join the game by scanning the QR code, but I only have prizes here. So for the online participants, if they are among the winners, and hopefully they are, they can collect their prize from me here in Toronto whenever they come here, if they are not here already. All right, so let's use another maybe 2 minutes for people to get to know each other, and then I prepare the game. So use this opportunity to talk to another person who you don't know, introduce yourself, and explain about why you're at this workshop. You're not a random selection of individuals. So the chances that you make a good friend here is much, much higher because apparently you care about some of the same things. Oh, wow, these are perfect. Excellent. Thank you so much. All right. All right, you can join the game by scanning this QR code. So hopefully also the online participants can see the QR code. Just scan it with your phone, and there will be multiple choice questions waiting for you. And I have prizes for the top 3. So those who answer more questions correctly and faster than others, I have some prizes for them. So if the QR code doesn't work for you, you can go to kahoot.it using your browser on your laptop, on your iPad, on your phone, and provide this game pin. All right. So raise your hand if you need more time for joining in the game. Yes, okay. You have time. And also, for those of you who joined a bit later, I have handouts of the workshop. Let me know if you need one. Who joined later, okay? Go. Go. Handouts. There you go. All right. Are you still selecting your character? Raise your hand if you need more time. Otherwise, let's start. More time? Yeah. Okay, enter. Oh, game pin. Yes, yes. So raise your hand if you have difficulty joining the game. For online participants, if you have issues joining the game, just type in the chat, and hopefully I can help you. All right. Okay, are you ready? So you need to, so those who answer correctly and answer faster than others get more points. And the questions are, some of them are typically controversial in my class. So sometimes students complain to me that, oh no, there are different interpretations to this. So when I say correct, it's more like aligned with what I said earlier, which doesn't really make it correct. All right, shall we start? Are you in? Yeah? Yeah, you're in. Okay. Just a practice run. Just to make sure that everyone knows how Kahoot works. So you just, select it on your phone. And the questions will be standard questions. Like one of them will be correct, all the other ones will be incorrect. But the direction of the question will be on top. Sometimes the direction says select the incorrect statement. And there are some questions, I think, it will show multi-select from the beginning, then you can select multiple options. All right. All right. Okay, so hopefully those 4 people also learned how this works. And this was just a practice run, so no scores, but the game begins now. All right, so it was machine learning. Okay. What are used for learning GPT-4 numerous parameters? All right, so it was 1,000 terabytes, not 1.8 trillion, right? And it was from news articles and websites. All right, I can see some competition going on. Convincing responses of GPT are. Okay, good. Sorry that some of these questions are just too basic for this audience. Multi-select, so you can select more than one option if you want. What task can GPT-4 do? All right, all of them were correct. Actually, these are all things that GPT-4 can do. Okay, and I guess this is the last question. Which statement is more accurate about AI? Okay, so I guess this was the controversial one, but yeah. So it was more about what was covered. Otherwise, we can debate more about it during the break. All right, let's see the winners. So in the third place, we have Lively Octopus. In the second place, we have Amazing Bunny. And drum rolls for the first place, Green Lemur. So, all right. So who are Green Lemur, Lively Octopus, and Amazing Bunny? Raise your hand. And also, if you're online, type in the chat, you know, which character you were, because I have prizes for you. All right. Who are the winners? Raise. I only see one hand. All right. So, Alexandru, if you come to Toronto, I have your gift. I have your prize. Come and collect it from me, okay? All right. There you go. From the Fields Institute, they gave us more support. I just sent an email like last night at 11 p.m. asking for prizes for this game, and they managed to give me prizes. So they are just awesome. All right, and for the honorable mentions, there were 2 people who got the honor mention, right? 4 and 5. So raise your hand. Okay. 4 and... Okay, so this is for you. This is about the timeless challenges of being a research supervisor from 500 years ago. All right, so I think we still have some time before the coffee break, right? Yeah, so I'm going to start the second part, and then maybe we finish it in 20 minutes or so. Okay, any questions so far? All right. Okay, so all right. Oh, stop share, screen share. All right. Okay. So, all right. So I hope all of you can see the slides. All right. All right. All right, so now we're going to gradually get to more technical details. All right, so these are some of the learning outcomes from part 2. we're going to do 6 different passes over, large language models and BERT. In pass 1, the learning outcome is being able to describe what language large language models are. Pass 2, you will be able to explain BERT as a machine with an input and output and use it in Python. In pass 3, you will be able to specify several use cases of BERT as a large language model. In pass 4, you can explain the attention mechanism and its significance. In pass 5, we will recognize 3 innovations used in the architecture of transformers and BERT. And in pass 6, we'll talk about pre-training and fine-tuning of BERT. So these slides contain material from various sources. Many thanks to all these individuals for making their materials publicly available. All right, let's start with pass 1. So you saw a Venn diagram earlier. Now we're not talking about generative AI anymore. Now we're talking about large language models, which are subset of deep learning. They are subset of machine learning, and machine learning is a subset of AI. So we already talked about, these common language tasks. So can someone remind us of what text classification is? Raise your hand if you want to answer, or type in the chat if you want to answer. Anyone? If you can explain text classification and give an example for it. No? Anyone wants to? Yes, please, go ahead. Categorizing text data in some predefined, classes, like positive and negative. Yes, exactly. So the no, topic modeling would be an unsupervised text or language task. So in topic modeling, we don't know what the topics are. So we have data and we want to do essentially clustering. It's more like a clustering, which would be unsupervised, but text classification is a supervised because we already know the classes in advance. Great question. Yes? Fact checking, I think it depends on the classes, right? If we define the classes in advance, I think we can consider it as a text classification. If we want to classify like text into factual versus non-factual, right? Yeah, I mean, question answering, I think, is more about how we package the whole thing and how the user interacts with the system. Of course, all of these can be thought as sort of, user dealing, asking the question from the AI system so that it is more interactive. But fact checking, I think if we have 2 classes, if we have factual and non-factual, we can think of it as text classification. But of course, it's a bit more nuanced than binary sentiment analysis, because typically, there are many non-factual things on the internet which are so convincing, or I mean, they are designed, as clickbaits and designed to be convincing, and yeah. All right, other questions? All right, so these are some language tasks, and large language models these days can handle all of them. So we talked about history of language modeling. So yeah, the thing with this, timeline is that it changes so quickly that every few months I need to update it. So actually, this last part, I mean, Llama 2 and Gemma, I had to add them very recently so that I wouldn't look like an outdated, out of touch professor, because my students, they know this stuff. They learn about this stuff much earlier than me. All right, so that was pass 1, just to get some ideas about large language models. Now we're going to talk about BERT. So BERT is a language model from 5-6 years ago. It was developed by a team of people from Google and here at University of Toronto. So at the very high level, you can think of this fancy machine as something very simple that takes an input like this. It takes text as input, everybody dance now, and as its output, it gives us this. It gives us a couple of vectors. So each, each column that you see in here is a vector. So BERT gives us one vector for the CLS token. We will talk about this later. It will give us one vector for the word everybody. So the word everybody, when it goes through BERT, it becomes this vector. It's a vector of 768 coordinates, and this solves, some of the difficult parts of the language modeling for us. Dance becomes this. Dance becomes this vector.
Is the vector dependent on the context, or is it always?
It is dependent on the input word at all, but also it depends on the context. Yes, it also depends on the surrounding words, and that's the advantage. Yes.
If I say I like dancing,
Yes.
then
Then
dance would be different.
would be different. Yes, yes. That's the important part. So when we go back to the to this, if I'm not mistaken, I think the word to vec didn't have context. So in 2013, we were also converting words to vectors, but they didn't incorporate the context in that embedding, right? So dance would always become the same thing, would always become the same vector. But now with the two examples that one of the participants gave, if we have the sentence, I like dance, and another sentence, everybody dance now, the word dance in the two sentences will be embedded, meaning converted, into two different vectors. All right, so as you can see, we get these vectors, and the length of the vectors is, this is 768 by 1. So it has 768 coordinates. Anyone wants to make a guess where this number comes from? Why 768? Mathematicians in the room can hopefully come up with some good guesses. Anyone? All right, so usually the length of these vectors are powers of 2. So we wouldn't be surprised if we see 1024 or 512, right? 2 to the power of 10 and 9. In this case, they were trying to compete with GPT-2, if I'm not mistaken. And GPT-2 back then had roughly 1 million parameters. They wanted to build a version of BERT that has the same number of parameters so that the comparison of performance would be apples to apples, would be fair, right? And in order for the total number of parameters in their model to be somewhat comparable to GPT-2, they ended up with this slightly unusual number, which is the midpoint between 2 to the power of 9 and 2 to the power of 10. All right, so, but how can we use BERT in Python? So this is just to show you how accessible, these models are. Of course, when we want to tweak them or we want to develop, something with the same architecture, it's a bit of work. But otherwise, for anyone who knows some basic Python, I would say they have access to the BERT model. They have access to, these language models. They've had it for 6-7 years. So despite how, how glamorous and kind of glorified they are rather accessible. So we can And what you see on the slide shows, 4 basic steps for accessing these models. So first, in Python, we import, these libraries. Then here you can see that I have loaded, BERT preprocess and BERT encoder, right? So these are like some pre-trained models that are available on TensorFlow Hub. TensorFlow Hub is like a website, like a repository for many of these, pre-trained language models and other neural networks. Then here you can see that I have a function. My function takes the input. The input is sentence. It takes the input. It applies this pre-trained model on it. Then it becomes this kind of intermediate output. Then it will apply this function on it. And here I'm returning the pulled output, which is, pulled output is this. If you have the sentence, everybody dance now, the output from BERT will be a couple of vectors. Here, I only care about this vector that I'm highlighting in purple. So the function you saw in Python would give us the CLS vector of the input sentence. And you might have guessed that CLS stands for classification. So if you want to do text classification, we can just take this output and give it to any classifier, logistic regression, random forests, any classifier, ideally something that doesn't suffer from curse of dimensionality, so something that has regularization or otherwise can handle high dimensional data. And then we have a classifier. So here is just an example to see this output. So if my input, if I have these two input, let me use a different color. So if I have this sentence, $500 discount, and even the dollar sign is on the wrong side, hurry up. And this other input, hi prof, will the exam be easy? Let's say these are, two, the content of two different emails, and we want to build an email spam detector, right? So there are two types of email, wanted email and unwanted email, right? So the emails I receive, essentially there are these two types. I get emails about discount and hurry up, which are just, spam, unwanted email. And sometimes I get, emails from stressed students asking me whether the exam will be easy. And definitely, I don't want them to be stressed, but I don't consider that as spam because I'm a good professor. So now you can see that each of these sentences will be converted to a different vector, right? This is the vector for $500 discount, hurry up. This is the vector for hi prof, will the exam be easy, right? Now, if we use these vectors as features or as predictors, and we also have labels for this. So we give the label of this one spam, and this one not spam, right? These are the labels. If we use the labels as dependent variable, the coordinates of the vectors as independent variables, and we give it to a logistic regression, it can do some text classification for us. This is supervised learning, so we need labels, right? This is for those of you with statistics background. For those of you who prefer a CS terminology, we use spam and not spam as Y, and we use the coordinates from these vectors as x1, x2, x3, all the way to x 768. Then we have 768 features and one response or one outcome variable. And we fit a random forest, or we fit a gradient boosted ensemble of trees, and that can do text classification for us. Yes?
Is it possible to identify some correlation among those vectors or features?
Yes, so the features are going to, here BERT does all the heavy lifting for us. So in terms of correlations, I don't know what would be the meaning of correlation between embedding of high prof will the exam be easy and the embedding of $500 discount. But my impression is that any two sentences which have some similarities to each other will get some sort of similar vectors. That's why this idea will work. There's, of course, I mean, it works up to an extent. You know, there's a limit to how useful this will be, but for many tasks, this will be just fine. Yes. Sorry, again, we need to use the microphone. I keep forgetting that part because for the online audience to hear us. And please make sure that the microphone is on. You can tap on it and see.
Will we eventually see that?
Is it on? Sorry, can you also tap on it just to make sure? Yes.
Will we eventually see that why we are choosing these vectors, as in?
Yeah, the whole point is that we are not choosing it. We rely on BERT to find the suitable vectors for us. And the suitable vectors is about separating the data. So if, for those of you who are familiar with support vector machines, the idea of support vector machines is that if we have data that is in low dimension, and it's difficult to separate them, so they are non-linearly separable, when we take them to a higher dimension, they become linearly separable if we go to a sufficiently high dimension. So here is an example. Let's say we have just two features. We have x1 and x2. These are two predictors. And let's say that, that we have two types. We have two classes, class positive and class negative. And they are, let's say, like these. Yeah. All right. So this is a non-linearly separable feature space. This is because there's no way that we draw one line in this feature space and separate x's from o's, right? Because they are on the same line. But if we just plot x1 and x1 squared, they're going to kind of follow this sort of pattern because this is the x squared function, right? So our data become like these. And for data like this, we can draw this straight line. The straight line separates circle, so this is circle, from x. So this is the idea that whenever we go to a higher dimension, the data gets closer and closer to being linearly separable. Here, we're using, instead of words, we're using vectors of 768. So in dimension 768, different sentences are further away from each other. They are sufficiently distant from each other to the point that if we want to do sentiment classification, we just need to find the line, the hyperplane, that separates positive and negative sentiment. In the same space, if we want to do, let's say, fact-checking, we just need to find the hyperplane of fact-checking, right? So back to your question, I think you asked me.
Sorry, I meant how are we choosing these vectors? Because I can see they are both negative and positive, and they are between -1 and 1.
The vectors, we are not choosing it. We rely on the idea of BERT to be a relevant idea, and we trust BERT to do it for us.
But how is BERT doing it? Like, is
In the next couple of passes, yes, you're ahead of the class. Yes, we will learn how BERT does it, and it's pretty intuitive and pretty smart. Yeah.
Thank you.
Yes.
Your earlier example about the food was adequate, but not
Yes.
how well do you think BERT can handle that?
BERT can handle it partly because the challenge of the word not. So, do you want to repeat your question for the online audience?
Yeah, your earlier example on the board about the food was adequate but not good, and but takes context into account. Right?
Yes.
So what are your thoughts on how
Yes.
well it can encode?
So the issue with the sentence, the food was adequate but not great, was that any architecture, any language model that doesn't take the context into account will kind of aggregate positive sentiments from different words and kind of combine them as an overall sentiment. The thing with that sentence is that the word adequate is somewhat positive, the word great is definitely very positive, and the word not is just a common word in the English language, so it will not kind of negate the effect of great. The language model, or the RNN, basic recurrent neural network, will not know that that not is related to great. So not will be disregarded, and the whole thing will not be classified as a negative. In here, BERT is going to have an attention mechanism. I'm going to explain it to you later, but it will allow BERT to see that when it is encoding the word great, it should pay a lot of attention to the word not.
So how about if you change the sentence to like the food was adequate and good? Do you think there would be a bit of difference in the vectors for that, or?
In the vectors, yes, definitely, because one of them is a positive, the other is a negative, yes. And it's not just being different, the idea is that every sentence will be sufficiently distant from every other sentence. And when they are distant, then it's just a matter of finding the hyperplane that does the task we want. Question here.
Given the fact that actually we can deal with very long sentences and sequences, right?
We can or we cannot?
We can, right? So we can give, 10,000 words to BERT and want them to give us a vector, right? So considering this fact, actually we might need sort of even larger vectors, right? To lead them. So is that possible that we allow BERT to give us even higher dimensional vectors in order to be able to distinguish the word and the larger sentences in order?
Yes, the length of embedding is something that we have control over. So the user can decide to use a different version of BERT, or use a version where this is where they can specify the length of the embedding vector.
Yeah, but it is fixed and specified in the, for example, this Google Translate, right? It's given fixed number, right?
So from TensorFlow Hub, you have access to, let's say, 100 different versions of BERT or more. And there must be a version where you can specify the length of the embedding vector.
Okay.
Yeah.
Depending to this length, actually, probably you're allowed to use certain length as a maximum of the text that you're giving to in order to.
Yeah, I wouldn't say that these two are directly related, but both of them are about the architecture of the model you use. So probably also the model we loaded here, there's a limit to the number of words.
But the fact that, well, if you allow the classification to have a lot of very, very long sentences, that the combination is so high that it is much, much more than the number of combination of these possible vectors. So the encoding, the embedding wouldn't get as distant as we want, right? So we need higher dimension, really. We want to deal with the lengthy text, right?
Yes, there's a connection between these two limits that you're talking about. Yes, there is a connection. And there are different flavors of BERT with different numbers, you know, different limits for the two things you mentioned, for the input length and for the output length. Yeah. There's another question there, if you don't mind.
Thank you. I missed a little bit, so sorry, I apologize if this was covered. So is there, I understand that there are kind of supervised versions of BERT that have been trained on certain data to operate in context. So I'm somewhat familiar with FinBERT, you know, in the finance context. But is it possible to have, so if BERT is aware of the context in general, is it possible to have multiple contexts? So almost like combining the idea that we're going to encode, but the encoding is going to be, say, a function of the topics that we extract.
Yeah, I think, so the thing is, like, there is no limit to context being one context or multiple contexts, because all of these kind of translate to mathematics. And eventually, how good or how useful the model is something that we can quantify, right? So as it is all about mathematics, I would say BERT is not limited to one context necessarily. And it's just a matter of how good the trained or fine-tuned model will be for the task that you have in mind. But I wouldn't say that there is necessarily just one context, like if FinBERT is only about finance and nothing else. Yeah. Other questions? There's a question in the back. Okay. Thank you.
My question is a little bit related with the context of finance.
Yeah.
If I understood correctly, I could get text from blogs or Reddit or Twitter, use BERT, I will get the vectors.
Yes.
And then, for instance, if I using text to identify manipulation practices in finance, I will train the vectors according to the keywords that I consider relevant for this subject, because BERT is not giving me that. BERT is just translating text to the vector.
So what you need, I mean, with the keywords, it would be more of a rule-based idea. But forget about the keywords for now. I suggest that you consider having a labeled data set, right? So if you have, let's say, I mean, again, it depends on the context and how good you want the final model to be. If you have, let's say, 10,000 pieces of text, and you use a reliable rule-based method to label them.
Yes.
Ideally combined with a human annotator to also kind of verify, let's say 50% of them or something, to make sure that they are being labeled correctly. Then you can get the vectors from BERT, get the labels you have, put them together. That would be labeled training data for classification. Then you can give that to random forest or gradient boosted trees or logistic regression, and you will have a fraud detection that handles text.
Okay, so that means it's not just related about the keywords, approach.
Yeah.
It's a different approach, but you can combine it.
You can definitely combine it because annotating, let's say 10,000, comments could be challenging, and there are many people who combine, sort of an automated version of annotation and a human annotator to verify that the quality of the training data is good. All right, so shall we go for the coffee break now? All right, so thanks a lot for your attention. In the second part, we're going to cover more technical details, and I'm happy to interact with you during the coffee break. And also for the online participants, please feel free to type your questions in the chat whenever you want. And ideally, if Pierre or someone else from the organization team sees the chat and just signals me, I can also answer their questions right away. Thank you very much, and see you for part 2 in half an hour.